A farmer checks the clear morning sky, expecting a full day of sun. By noon, 6 storm clouds roll in and halt production. Everyday life is governed by unpredictability. We face the exact same uncertainty in human events. A local football team might step onto the pitch with a perfect record, but fans still question the outcome of the match until the final whistle blows. We cannot predict these outcomes with absolute certainty. What we do have, however, is a precise mathematical system designed specifically to measure their likelihood. Insurance companies calculate your monthly premiums, how meteorologists track storm systems, and businesses manage their financial risks. This lesson introduces the probability scale, a framework used to translate these uncertain moments into specific, usable figures. This diagram represents the probability scale. Every event exists strictly on a spectrum between 0 and 1. At the far left, a value of 0 represents an impossible event. If you roll a standard 6-sided die, rolling a 7 has a probability of 0. It simply cannot happen. On the far right, a value of 1 means absolute certainty. An inevitable natural event, like the sun rising in the east tomorrow, has a probability of exactly 1. Right in the middle is 0.5, representing an event equally likely to happen or not. A standard coin toss lands right here on the scale. To calculate where an action lands, we first identify the sample space, the complete set of all possible outcomes. For our coin, this is limited to heads and tails. An event is the specific outcome we are testing for. If we want heads, we are isolating one specific event out of 2 total possibilities. 1 divided by 2 anchors us exactly at the 0.5 mark. Defining your sample space and isolating your event is the strict prerequisite to mapping any scenario onto this 0 to 1 timeline. Here is the mathematical formula that drives the scale. The probability of an event is the ratio of successful outcomes, divided by the total number of possible outcomes. Let's test this formula with a physical example. Look at this open canvas bag. It contains a total of 5 bottle caps. 3 are red and 2 are blue. If you reach in blind, what is the probability of pulling out a red cap? We input our 3 successful outcomes, the red caps, and divide them by our 5 total possibilities. That yields a probability of 0.6. We apply the same logic to the blue cap event. 2 successful outcomes divided by a total of 5 possibilities equals 0.4. Because probability relies on ratios, these calculations can be expressed correctly in 3 distinct formats. Fractions, decimals, and percentages are completely interchangeable. Mastering this simple ratio allows us to take a physical scenario and accurately plot its likelihood on paper. Human intuition frequently misinterprets these mathematical rules. People commonly fall for the gambler's fallacy, the belief that if you flip 5 heads in a row, the next coin toss is somehow mathematically due to be tails. This belief fails because it ignores the concept of independent events. A coin has no memory. The results of previous flips have 0 mathematical impact on future separate actions. Because the physical coin remains exactly the same, the sample space never changes. The probability of getting heads or tails resets to 0.5 every single time it leaves your thumb. The probability formula also has strictly enforced boundaries. Because your successful outcomes can never outnumber your total possibilities, calculating a probability of 1.5 is mathematically impossible. Trusting the math of independent events protects our analysis from the flawed intuition of human bias. We can verify this logic right now. Look at this box containing 5 red pens and 3 blue pens. What is the probability of picking a blue pen without looking? First, you define the total sample space, 8 pens. Then, isolate your specific event, 3 blue pens. The correct answer is B, 3/8. Probability requires active calculation. Keep practicing these concepts with everyday objects, like dice, coins, and playing cards. Over time, the math becomes second nature. Understanding these ratios provides a framework for measuring the risks we encounter every day.